Good morning, everybody. We usually have a do now, but since we're going to do exam review, we're going to skip the do now and go over kind of prerequisite science skills and chapter 2 stuff after we go over some of the main points of chapter 3. I'm sure that a good number of you probably didn't have time to look at the chapter 3 video. That's okay. I'm going to go over kind of the big details that I think we should go over as a class, but just giving you the warning now, there is more to chapter 3 than what we cover in this lecture today. So you're definitely going to have to make up some of that. It's not difficult. Chapter 3, there's no math. It's really all concepts, and a lot of it you've already had before, most likely, either in high school chemistry, maybe a little bit of physics because we talked about different types of energy. But I promise it's not that bad. Make sure that you check out the video. So with that said, we're going to get started now and jump into chapter 3. So the first big thing that's covered in chapter 3 is the different states of matter: solid, liquid, gas. I am certain that you have heard of those before because you're in college now. But what we need to do is give you a little bit more vocabulary and some more details about the characteristics of these states. So I'm going to kind of go ahead and fill in this table. You can fill in the table on your own if you would like, if you got a chance to watch the video. But while I'm filling in the table, I'll talk about these characteristics for solids, liquids, and gases, and that'll get you caught up. So for the properties we'll cover, we've got shape, volume, compressibility, and energy. We'll start with solids. Solids are just that, they're solid. They're not going to be necessarily flexible to kind of change their volume or shape very easily. So if a solid is in a particular shape, it's fixed, right? The same for the volume. We're not really going to be adjusting the volume unless we're breaking the solid apart. Also for solids, they don't really compress. So we'll say not significant here. And in terms of energy, this is referring to the kinetic molecular theory, which pretty much says the further apart particles are, the more energy they have. So with that said, solids are packed really tightly. The particles in a solid are packed really tightly. They're very close together. So while there is some kinetic energy, it's very low in comparison to the other states of matter. Move on to liquids. The shape of a liquid, volume of a liquid. So the shape of a liquid is not fixed. It's variable. You can take water, right? Let's say you have 100 milliliters of water, and you can put that into a graduated cylinder that's very tall. You can also pour that 100 milliliters into a very short cup or a shallow pan. So the shape of the water will change depending on the container that it's in. But the volume does not. It's still 100 milliliters in each of the containers you put it in. The shape just changes. Does that make sense about the difference between the shape and the volume when we're talking about a liquid? I know it is an early morning. 8 a.m. strong. 8:05, and we're already almost 2/3 of the way through a slide. So good morning for those of you who just joined. Okay, so one more time. I got it one more time. Shape versus volume. Let's say, I'm going to start drawing. You asked me one more time. I'm going to start making these terrible drawings that I do. There's my graduated cylinder. And it's got water in it. Say 100 milliliters. The shape of the water is like the graduated cylinder, right? I could also take that same water and put it into a shallow dish. Now, it doesn't really fill that much because it's only 100 milliliters of water. Same volume, but the shape of the water is different. It's flat and kind of laid out. Does that make sense now? Okay. So that's the shape and volume of a liquid. The shape is variable. It varies with the container. The volume is fixed. Just like solids, you're not going to really be able to compress a liquid. And its energy, we'll call it medium. It's kind of in between. The particles are not tightly packed like a solid, but they are close together. The particles in a liquid are able to flow past each other, but they still interact. So they're close, just not as tightly packed as a solid. Now we're going to move on to gases. Gases are a whole different ballgame. We're going to spend a whole chapter on gases towards the end, actually at the very end of the semester. So we're not going to dive too much into gases, but we will revisit them and talk about them more than you ever wanted to in chapter 10. For gases, the shape and volume are both variable. The shape of the gas depends on the shape of the container, and so does the volume. A gas will expand or compress depending on what the container is. So for compressibility, it will absolutely compress, and it is significant. It's something that we care about. It's also got the highest energy because its particles are the farthest apart. Gases move very quickly, and they are so far apart that we assume that they don't really interact with each other. The particles in gas, they just kind of zip by each other, bounce off of each other. They don't care. They have such high energy that that's what they do. I talk about this in the video, and I go through each category in length. So again, make sure that you check out the video because we are not going to cover every single detail. Chapter 3 is a lot of vocabulary, and you just have to memorize it. Thankfully, a lot of it is stuff that you've probably heard already, or at least it makes sense. Like, oh yeah, okay, that makes sense. So make sure that you watch that video. Are we good with this table? There's a table very similar in the video and in the lecture notes already. So if you're like, there's already another table that also has really good information in it. So let me know if we're ready to move on. So we covered the different states of matter: solid, liquid, gas. There's some terms that we need when we want to talk about the changes of state. So to go from a solid to a liquid, liquid to a gas. I included this blank slide in the lecture so that you can kind of quiz yourself. And I also have the filled in one with the nice pretty pictures and everything like that. We're going to go through and fill this in. Most of it you already know, but it'll hopefully be a good refresher. Let's use an example of a solid, liquid, and a gas. We'll use H2O, right? So as a liquid, that's water. As a solid, it's ice. And as a gas, we'll call it steam or water vapor. So those are 3 examples. If I have ice and it turns into water, what does that ice have to do? And this is not a trick question. When ice goes from that solid to a liquid, what is it doing? It's melting, right? What's the opposite of melting? Freezing. So when we increase our temperature, we go from ice to water. That's melting. So you need to increase the temperature. You're adding heat to transition from a solid to a liquid. Let's say we have the liquid water and we want to make steam. That's the gas. What do we call that? That process. Think about if you're going to make some pasta. It's what you do with the water. It's got to boil. So this is where evaporation comes into. There is a difference between evaporation and boiling. So boiling is the whole pot. You see them big old bubbles coming from the bottom all the way up to the top. Evaporation happens just to the very surface. So the very surface of the water, some of those water molecules are able to escape and become vapor. If we're going from a gas back down to a liquid, we're going to condense. So if you have, let's say that you like to keep your apartment or your home really warm in the winter, and you have high humidity because you're running a humidifier or something like that, you might have some condensation on the glass on the inside because the temperature differential outside is cold, inside it's warm and moist. So you might have some moisture on that glass. That's condensate because the water in the air is condensing, it's cooling down to become a liquid. Now we've got 2 more states to talk about. In some cases, you can have a solid that goes directly to a gas and skips the liquid state. And likewise, you can have a gas going directly to a solid. To go from a solid to a gas, that's called sublimation. And the opposite of that is deposition. So those are 2 new terms that you might not know. One example of a substance that does this is carbon dioxide. Dry ice is solid CO2. It's very cold stuff. But if you just sit it on the countertop, you don't have a liquid mess. It just goes directly to a gas. So if you've seen any movie that has, all those flasks and beakers with the colorful stuff and there's smoke and steam, and it's just food coloring in water with some dry ice added to it. That's it. So that's an example. You might see this if you've ever done food service with like ice cream. This is used sometimes to keep the ice cream cold when it's, being shipped from one place to another. But that's it for physical changes of state. Any questions here? Really? So the next topic we need to cover is classification of matter. I went through this in the video. I'll kind of give you a brief overview so that we can do a little bit of practice together as a class. This flowchart is going to be really handy for helping you remember the relationships of all of these terms. So if you didn't get a chance to look at chapter 3, when you do, make sure that you have a flowchart like this in your notes. And when you're studying for the next exam, recreating this flowchart will help you too. So we're classifying matter. Everything that has mass is made of matter. So matter makes up all the things. We can split matter up into two different categories, mixtures and pure substances. Mixtures they're made up of at least two substances and can be physically separated. So examples of physical separation would be to boil something, to filter something. Those are examples of physical separation. You're not doing anything to change the chemistry. You're just manipulating the substances to separate them. That class, mixtures, can be split into heterogeneous and homogeneous mixtures. Heterogeneous mixtures, you can clearly see that there are two substances or more. So in the example here, we've got water and oil. You can see the oil floating on top of the water. Very easy. You don't need to do anything to see, oh, look, there's two different things in this container. Another example would be sand in water. Pretty much any solid in water, right, that doesn't dissolve is going to be a heterogeneous mixture. A homogeneous mixture is one that you can't see. You can't see the components, but you can still separate them physically. One example of that is salt water. So what's shown here is an IV that's got 0.9% sodium chloride. It's still salt water. If I sat a glass of salt water next to a glass of regular drinking water, you wouldn't be able to tell them apart until you took a taste. That's a homogeneous mixture. It would be the same thing with sugar. Sugar dissolves in water. You wouldn't be able to tell the difference unless you tasted it. But you can still separate the sugar or the salt from the water. You can heat it, or you can just leave the cup out and let the water evaporate off. Eventually, you'll be left with just the salt or just the sugar. So how are we with mixtures? Do these definitions make sense? Now, we can get to pure substances. Yeah, it's a lot to just take on and be like, oh yeah, everything makes complete and total sense. So you'll have to go back and kind of review it. If we took a mixture and separate it physically, then we could end up with pure substances. Okay. Pure substances, they have a definite composition. Which means that it's always made up of the same stuff in the same way. Compounds, you can chemically separate into elements. So if you think about compounds as combinations of elements, and the details that I'm giving you here, these are not formal definitions. I give those in the video, and it's in the lecture notes. But this is kind of the layman's terms, get you rolling so we can do a little bit of practice type of definitions. So compounds, think combination of elements. So like H2O. We're going to talk a lot about water. That's a compound. It's got hydrogen and oxygen. Elements, it's everything you find in the periodic table. And there's nothing you can do to further break down an element by chemical means. So examples of elements would be gold, carbon, hydrogen. All of those are elements. So now what I want to do is a little bit of practice to give you a flavor for what you're going to be expected to know for your homework and for the exam. And remember, Chapter 3 is not on your first exam. Chapter 3 will be a part of exam 2, so don't worry. We're going to label each one of these as a compound, element, or mixture. And for the mixtures, we're also going to label it as heterogeneous or homogeneous. So the first one, we have sodium metal. This is where you need to know your elements, or at least have a periodic table handy. Sodium is something that's listed on the periodic table. So that is an element. Sodium chloride. This is table salt. What do you think it is? Do you think it's a compound, element, or mixture? It's a compound. It's made up of two elements. You can't physically separate the sodium from the chloride. You have to do it chemically. So this is a compound. What about salt water? Compound, mixture, or element? It's a mixture. I just gave that example. It's definitely a mixture. But now we need to label it as heterogeneous or homogeneous. And the difference between them is with heterogeneous, I can look at something and see the different components in it. Homogeneous, I cannot. So if I look at some salt water, can I see that there's salt in it? The answer is no. So it is homogeneous. Does everyone get that distinction? I'm sitting here doing all the hand movements, and I'm like, nobody sees me. I'm so used to teaching in person. I'm a very visual, hands on, physical type of instructor that it is driving me crazy sometimes to do this remotely. But maybe you can hear that I'm moving. I don't know, but I am. Okay. Now we have brass. Brass, if you don't know, is a combination of copper and zinc. And if you think about brass instruments, trumpet, trombone, that's where they get their name from. It's what makes up a trumpet or a trombone or some of these other instruments. Do you think it's a compound, element, or a mixture? This one is a little bit tricky. It's actually a mixture because you can physically separate these two. If you heat it, these two metals have different melting points. So you can physically separate them. It's not a compound, it's a mixture. And if you were just looking at it, you wouldn't be able to tell that it's a mixture of metals. So again, this is something that's homogeneous. Last one, we have a piece of metal in water. Compound, element, or mixture? It's a mixture. And is it heterogeneous or homogeneous? Mm-hmm. You can absolutely see the two. You can see the two components of a piece of metal in water. So these are the kinds of questions you'll need to be able to answer for your homework and on exam 2. I know you're not going to be able to do this, there may have been some question marks since we're just going over it really briefly, but I wanted to give you an idea of the types of questions you'll need to answer. Is everybody clear on kind of expectations for classification of matter and what you're expected to know and be able to do? Good. Next, we've got metals versus nonmetals. So most of the periodic table contains metals, but there are some what's called semi-metals or metalloids and nonmetals. I have listed here the general characteristics of metals and nonmetals. There are always exceptions, but in general, metals are going to be solid at room temperature, have like a metallic luster, which means shiny. They are very malleable and ductile. You can extrude them into, long, thin wires and do all the things. You can hammer them, they won't break. So that's very malleable, pliable. They conduct heat well, density and melting points are usually very high, and they react with nonmetals. For the characteristics of nonmetals, just think the opposite of metals for the most part. So the appearance is dull, they're brittle, they're not conductors of anything, low densities, low melting points. That's nonmetals. You'll need to know these characteristics. So if I say that an element is shiny in appearance and highly malleable with a high melting point, you should be able to tell me that that element is likely a metal. Likewise, if I say something is dull and brittle, not a good conductor of heat or electricity, you should be able to say, okay, that's probably a nonmetal. Does that make sense? So I'm not going to dwell too long on this. It's in the video. Y'all can read. I'm going to leave it up to you. The periodic table. We're just getting a very small taste of it in Chapter 3. We're going to really dive in Chapter 4. But for now, what I want you to know is the periodic table contains all the elements that we currently know about. We're adding more and more. They don't really have official names yet, but I digress. Most of the elements are metals. And that's going to be the left-hand side of the table for sure, but it kind of, it's more than just the left-hand side, but we'll say the left-hand side. Because you'll need to know in general where the metals are, where the semi-metals are, and the non-metals. The non-metals, which on this periodic table, you have the metals in purple, the non-metals are in yellow, and the semi-metals are in green. The one that I will provide for you for exams, starting with exam 2 and beyond, is not going to be color-coded like this. It will, however, have the names of the elements spelled out and a little bit more information on there for you. The nonmetals are on the right-hand side. And the semi-metals, those have the characteristics of a combination of metals and non-metals. Talked about it in the video. We didn't really cover it here. There's not a whole lot to cover. But it's really, you can't call it a metal, you can't call it a non-metal. It's somewhere in between. And rightfully so, they're sandwiched in between the metals and the non-metals on the periodic table. All of the elements on the periodic table are arranged in increasing atomic number. So that's this little number in the top left-hand corner. That's the atomic number. Each element has its own unique symbol. Some of them have one letter, like in the case of hydrogen, and some of them have two letters, like in the case of helium. If there's two letters, the first one is capital, the second one is lowercase. I'm not requiring you to memorize the names of the elements. You'll get a periodic table that has all the names. You don't really need one for the first exam. But like I said, second exam forward, I'll provide you with the periodic table. And I'll post one on Blackboard and course content for Chapter 3 so that you have it when you're doing all your homework and stuff. Questions about the periodic table? So now we're going to get into something a little bit more active. We're going to talk about chemical formulas. So I'll do an example, and then I'll have you guys do an example. For these two problems, we have to state the composition of each molecule. So we have to write what atoms there are, and then how many of each atom we have. So in citric acid, we've got this for our chemical formula. We see all the symbols from the periodic table. When we state the composition of each molecule, you have to go through and literally count how many of each atom type there are. So I see C, H, and O. That's carbon, hydrogen, and oxygen. In order for us to know how much, we have to see these subscripts, those little numbers. It's called a subscript. It tells you how many of each atom you have. If you don't see a subscript, like in the case of here, there's no subscript, then there's only one. So if I were going to see how many carbons we have, I've got that C3, which means I've got 3 carbons there. Plus, I've got this carbon here. But it's in parentheses, and there's a subscript on the outside of the parentheses. So just like in math, if I had 3 times x plus 5, then I would have to distribute that, and it would become 3x plus 15. It's the same thing with the subscript on the outside of the parentheses. Everything in the parentheses, you're multiplying by 3. So I look at the carbon, I've got no subscript here, so I assume that it's a 1, but I have to multiply it by 3. When there's no subscript listed, you count that atom as one atom. So now my total carbon count is going to be 6. Now help me with the hydrogens. Take a second and count up how many hydrogens there are. You could put your answer in the chat. Okay. So we've got 4 here. plus there's 1 right here. And then we have the same thing where we've got 1 hydrogen on the inside of those parentheses, but we have to multiply it by 3. So that gives us a total of 8. You have to find all of the H's and total them up. They're not all going to be listed in the same place necessarily. What about the oxygens? How many oxygens do we have? So we've got that 1. And then we've got 2 of them in parentheses. So we have to multiply 2 times 3. And that gives us 7. So that is how you write up the composition of a molecule. It's not difficult. You just have to make sure that you're paying attention to detail. Any questions there? Okay. So this second one is pretty straightforward. Everything is listed and there are no parentheses or anything like that. We've got 27 carbon atoms. "46 hydrogens. And there's no subscript here, so we assume there's only 1. 1 atom of oxygen. So make sure that you understand how we got those answers, because you'll need to do it for your homework for Chapter 3. Which your homework for Chapter 3 is not due this Sunday. Giving you a little bit of a break, but you'll have to have Chapters 3 and 4 due at the same time. So I would recommend you work on it, but I'm not going to have it due until a couple of weeks from now. So we're still working on chemical formulas. Now we're going to take the number of carbon atoms and hydrogen atoms and all the other elements and write a formula. To do that, all you're going to do is look at what elements you have, right? In this one, propanol, I have 3 carbon atoms, 8 hydrogen atoms, 1 oxygen atom. You write down the symbol for the element, so carbon is C. And then however many you have, if you have more than 1, you write as a subscript. Hydrogen is H. So I'm going to write that as 8, H with an 8 for the subscript. Oxygen is an O. There's only 1 of them, so I just write O. Everybody understand how I got that? Okay, so I want you to take a minute and write down what lysine is in your notebook. I'm not going to have you put it in the chat because you can't really do the subscripts. But take a minute, write it down, and then I'll write it out on here and you can compare your answer. All right, So lysine is an amino acid. It's essential for making proteins in your body. We've got carbon, hydrogen, nitrogen, and oxygen. C6, H14, N2, O2. So that's how you write a chemical formula from the composition. Everybody good here? Yeah. It's pretty simple. Now we're going to talk about physical properties and physical changes. Then we'll talk about chemical properties and chemical changes. And then I think it'll be about time to take a break. So we've been talking about matter. We talked about the states of matter. We talked about how we go from one state of matter to another. So the physical changes of state. Talked about all the elements and how we can represent them as compounds. Now we need to talk about the different properties that elements and compounds can have. We can talk about physical properties and physical changes. A physical property is pretty much you're looking at appearance, density, melting or boiling points. We're just talking about the characteristics of a given element or compound. So if you were to make a dating profile for water, you would describe what it looks like. It's a liquid. It's made of hydrogen and oxygen. Its melting point, its boiling point. That's what it is. So if you were to describe something, how would you describe it? What color is it? What does it feel like? Is it brittle? Is it shiny? Those kinds of things. That's a physical property. A physical change, we're talking about one of two things. A change of state, meaning solid to a liquid or gas to a solid, something like that. Or a change in shape. So it could be that something has been cut in half or something like that. You will need to know the difference between physical properties and physical changes and be able to identify whether something is a property or a change. So let's try to do that now. Good conductor of electricity. Do you think that's a physical property or a physical change? Yeah, this one's a property. You could put P or C when we do this. Oxygen gas is compressed. That's a change. That's a change in its shape, right? High melting point. Property or change? It's a property. Melting ice. Property or change? So I want you to notice something. For all of the ones where we said it was a change, we've got some kind of verb. Is, compressed, melting. Those are verbs. So generally speaking, when you see a change, whether it's physical or chemical, which we're going to cover next, there's usually some kind of a verb. Whereas with the properties, it's their adjectives, their descriptors, but there's no action happening. So if you're a little bit confused about whether something's a property or a change, see if there's a verb. If there's no verb, then chances are it's a property. We good with physical properties versus physical changes? Then let's do chemical properties and chemical changes. Just like physical properties, chemical properties were describing what a substance can do. We'll call it the chemical capabilities. A chemical change is just a chemical reaction. The difference between these two is that usually you'll see that a substance can, and then there's some kind of, chemical reaction. Whereas with a chemical change, it's you have substance changes color, or burns, or combusted. You're going to see some kind of an action word. Just like with the physical changes. So with that said, let's try to classify these as chemical properties or changes. You could put P or C just like y'all were doing before. So gasoline can combust with oxygen. Property or change? It's a property. We're talking about what it can do, the possibilities of gasoline. A burning candle, is that a property or a chemical change? It's a change. A banana turns black, property or chemical change? It's a change. Reacts with strong acids and bases. It's a property. So you'll need to be able to distinguish between these two. And also, I could ask you, is this a physical change or a chemical change? A chemical property or a physical property? So you'll need to know all four and know the difference. Everybody good on those? Okay, that's all we're going to cover for Chapter 3. There is more to Chapter 3 than what we covered today. I wanted to leave room for us to do exam review. It's the first exam. There might be some anxiety. You might have more questions than you normally would about how the exam is going to work. So I wanted to leave space for that. Chapter 3 is not a difficult chapter. Like I said, most of it is learning vocabulary and being able to do matching and kind of identifying things, classifying things like we just were doing. I'm putting that more on you so that we can have more time for exam 1 review. Make sure that you review the lecture that is posted on YouTube and complete all the Chapter 3 assignments on Mastering Chemistry by Sunday, February 28th. I'm giving you a little bit of a break. This is your first exam this week. I know you're going to be studying for that. And then it's going to be Saturday, and you're like, maybe I should do some chemistry. Oh, it's due tomorrow. And maybe you got to work, you got other classes. So I recommend that you start the Chapter 3 homework right away. Start it this week, maybe after you take the exam. The exam will be available tomorrow. Read through the notes, watch the lecture, and start the homework. It's not due until the 28th, but your Chapter 4 homework is also due on the 28th. So you don't want to be trying to do 2 chapters worth of homework and quizzes on the same night. Everybody clear on what we're doing for Chapter 3? Are there questions about the exam? Logistics of how you're going to take the exam? Because this is kind of we're about to go on break, but I want to get the logistics questions answered first, and then when we come back, we do exam review. So just to refresh you what we said. Yes, the exam will be administered through Respondus Lockdown. So if you do not have Lockdown on your computer, you need to get it. If you have a Chromebook or you know that your computer don't do right with Respondus, then you need to make sure that you get the appropriate laptop or something, borrow somebody's. So what I do for the exams is, instead of giving you a time limit, you have to do it in one sitting. Everybody works differently, and some students have, certain requirements for time and a half and things like that. So I'm not going to hold you. Most people will get it done within a certain amount of time anyway, but I just ask that you get it done all in one sitting. So yes, I'll go over. So let me go over the basics here. For the exam, you will need a scientific calculator, not your phone. You need a scientific calculator. You can also have some blank scratch paper, and a pen or a pencil. There's also the equation sheet, which is posted in the Exam 1 folder, which is already in course content right now. So those are the 3 things that you can have. I also make a scientific calculator available through Respondus if you don't have one. To navigate to the exam, you're going to open Blackboard in the Lockdown browser. So don't open up Firefox, don't open up Chrome or whatever you use. Open up the lockdown browser and navigate to Blackboard. Go to course content and click on that exam 1 folder. It's already there, you just can't see an exam. Come Wednesday, tomorrow, you will see an exam. Click on it, get started. Make sure that you print your equation sheet before you do all this other stuff. So make sure you print that before you go into the lockdown browser and stuff. The exam will be available Wednesday through Friday. So it'll be available Wednesday at about 9 a.m. and it will miraculously disappear like it never existed at 11:59 p.m. Eastern Time. So you need to start the exam before it disappears. These are multiple choice questions. Some of them are fill in the response, or you have to put in a numerical answer. For the math problems, if you show your work, you can kind of type in your work or what your plan was. Then when I go through and grade your exam, if you don't get the answer right, I may be able to assess partial credit. So show your work in those boxes if you want the potential for partial credit. If you just have an answer, it's going to be right or wrong. If you have an answer and you show your work, then I may be able to work with you. That won't be for every single question. Like if it's a question on sig figs, well, you either have the right number of sig figs or you don't. There's no partial credit there. So I will post on Blackboard where you can find the lockdown browser along with the starter thing. The quick start guide. How many questions is it? I don't remember, to be honest. It's not going to be 100 questions. It's going to be like maybe 15. Don't quote me on that, but it's not going to be a super long exam. Other questions about the logistics of the exam. Again, if you have a Chromebook, if your webcam is cracked, if your microphone don't do right, make sure that you have access to something else that will work. This is a closed note exam. So you have your equation sheet. And what I would recommend is once you start the exam, jot down stuff on your equation sheet. So that's one good test taking tip. If there's a concept that you always get confused in your head, have that concept set and then jot it down right when you start the exam. There's no harm in jotting down some notes to yourself in that exam setting. You just can't bring your notebook to the exam. But if you know there's a couple of things that you're like, man, I always flip this around, or I need a sample of how to do a conversion problem, that's fine. You can write out on your stuff in the exam, like you started the lockdown browser, you're in exam mode, write down those couple three things or whatever it is to keep it straight in your mind so you can refer to that. But don't bring your whole notebook and all your notes and the printed lecture slides. We can't do that. Other questions? Okay. So I will post, like I said, about how to get Respondus lockdown. Yes, you can just write all the equations down. Just copy down the exact equation sheet onto a piece of paper. If you can't print it out, it's fine. I will post how to get the Respondus lockdown browser and the quick start guide. When the exam is available, I will put out an announcement. If you have any questions, you can think about them while we're on break and bring them up. Otherwise, we're just going to do exam review. So it's up to y'all. This is the time where we can do a break. If you want a break, we can take maybe about 10 minutes. Or we can keep trucking, do exam review, and probably end a little early. So y'all let me know what you want to do. Take a break or keep going. All right, then we'll keep going. We will keep going. So I wanted to make sure we hit on some of the questions that we didn't exactly cover the topics in class. And I put out the announcement last night saying, hey, you might want to have that equation sheet handy. So if you don't have it handy, go to Blackboard now and look in that exam 1 folder. Make sure that you know where it is because you'll need to know for the exam. But get that equation sheet and open that up because you'll need it. This is a question about heat versus temperature. We've got 2 beakers, one that has 50 milliliters of 40-degree Fahrenheit water, one that contains 50 milliliters of 40-degree Celsius water. And the question is, which one contains more heat? We didn't cover this specifically in class, but I did cover the topic of heat versus temperature in the lecture video on YouTube. So a couple of concepts. Temperature we talked about. That's the average kinetic energy of a particle in a system. So a system could be a beaker of water. The average kinetic energy that one molecule of water has in that beaker. That's the temperature. The heat is the total energy in that system. So if you were to take all of the particles of water in that beaker and sum up all of their energy, that is the heat. It's the total. So when we're looking at the heat, we're looking at, if I've got these 2 beakers, and they both have 50 milliliters. But they're at different temperatures. Which one has more heat? The total system, we're talking about 50 milliliters at 40 degrees Fahrenheit versus just the temperature alone, 40 degrees Fahrenheit. Temperature alone, that is the average kinetic energy. But when you say all the energy from all of that 50 milliliters of water, that's the heat. That's the total energy of the system. Imagine these beakers are the same. So how would you solve this problem? You've got two beakers with the same amount of water and different temperatures. In order to compare them and say which one has more heat, you need to have them on the same temperature scale. So you've got to take one and convert to the other. So you can convert Fahrenheit to Celsius or Celsius to Fahrenheit. But either way, you have to convert one of them so you can actually compare apples to apples. With that foundation, I want to give you guys 3 minutes to try this problem. So you have to convert one of these temperatures and then figure out which one of these beakers has more heat. So we'll call the 40 degree Fahrenheit one A and the 40 degree Celsius one B. As you finish and you figure it out, you can put your answer in the chat. Which one has more heat, A or B? I'll check back in 3 minutes. Alrighty. So for this problem, I chose to just convert Celsius to Fahrenheit. When I did that, I got 104 degrees Fahrenheit. So now we can compare apples to apples. 40 degrees Fahrenheit versus 104. It's no contest. B has more heat. So same volume, different temperature. With these questions, it's not going to be difficult. You just have to pay attention to detail. The key was seeing that you had a difference in temperature, 40 degrees Fahrenheit versus 40 degrees Celsius. If you thought that they were both the same, then you'd be like, what? And you'd answer it incorrectly. How do we feel about that one? Well, let's keep it pushing. This is a conceptual question about density. It was on the exam review. I always like to go over this question because there's usually some confusion and you think it's harder than it really is. You've got a tall glass cylinder that contains water floating on mercury. A piece of metal is resting on the bottom of the cylinder. Which of the following choices could represent the density of the piece of metal? Let's draw this out. So I have my mercury down at the bottom. and its density is 13.6 grams per milliliter. Mercury is a metal, but at room temperature, it's one of the weird ones. It is actually a liquid. And then we've got water, and its density is equal to 1. We've got some piece of metal sitting in the bottom. The water is sitting on top of the mercury, and the water is less dense than mercury. So, would you expect the metal piece to be more dense than mercury or less dense than mercury? Other thoughts? I want to see what more of you guys are thinking. Yeah. So that metal piece is going to be more dense than mercury. So now going back to the question, which of the following choices could represent the density of the piece of metal? What's your answer? A, B, C, or D? D. It's the only one that has a density that is greater than the density of mercury. So this is a conceptual question. You don't have to do any calculations. You will see a question like this on the exam. Not a matter of if, but when you see it. Remember, it's a conceptual question. You don't need to start getting out your calculator and trying to figure out density equals mass over volume. Not that type of a question. Everybody cool with this one? Now we've got a specific heat problem. I'll give you 3 minutes to read through the question and start working on your answer. Then I'll come back in and start setting it up and we'll solve it. If you have an answer, you can feel free to put it in the chat. If you're still working, that's cool. There is an answer key. So I'm pulling these. Some of these questions are from the exam review, which I posted. I've also got a couple of fresh ones. So if you're like, this looks suspiciously familiar, yes, this is from the exam review. So you've got a 12.6 gram metal sample. Initial temperature is 25 degrees Celsius, heated to 32. And the amount of heat gained by the metal was 125 joules, which is a very small amount. Calculate the specific heat of the metal. When you see specific heat, you should automatically be thinking about this equation. So C is specific heat, Q is the energy, M is the mass, delta T is the change in temperature. We don't know what the specific heat is. That's what the question is. The units for specific heat are joules per gram degree Celsius. So that's what we're trying to find. Our Q is 125 joules. M is 12.6 grams. And delta T, that is the change in temperature. So you take the final temperature and subtract the initial temperature. So far, all we've done is just set up what our variables are. Is everybody with me so far? Great. All we have to do for this one is just plug in the numbers. We've got 125 joules over 12.6 grams times 7 degrees Celsius. So our calculator is going to tell us some number with a bunch of digits. What we need to do is look back at the problem and see how many significant figures we have for each of these. How many sig figs do we have in our Q? We've got 125. How many sig figs? We've got the same number of sig figs for our mass, and each of our temperatures, 32.0 and 25.0, how many sig figs do those have? Each of these has 3 significant figures. So remember, if you've got a decimal number, we're starting with the non-zero digits here. Everything after this is significant if there's a decimal. So each of those temperatures has 3 sig figs. That means we've got to do that for our answer. If we round to 3 sig figs, that's 1.42, and then units, joules per gram degree Celsius. Sure. M is mass, and delta T is change in temperature. And I can kind of highlight each one of these so that you see where it is. Mm, I'm going to have to do an underline for the last one so you can match it all up. Yes, always include units. So some of these questions will be multiple choice, so the units will be there, but you have to make sure that you choose the one that has the correct units, not just the correct numerical answer. I'm not going to try to trip you up, but that's something that you should always be looking for. When you're entering an answer, like a short answer kind of deal, make sure you include the proper units. You will lose points. You will not get full credit if you do not have the full answer, which includes units. You're very welcome. We ready to move on to the next question? I don't have another one of these, and I think that here's what we can do. I'd like to get through the rest of these problem types so that we don't spend too much time on any single one. And then if we have time to circle back around, I can make up another one for you. Is that fair? All right. How many picometers are in 2.55 times 10 to the 8th kilometers? I made this one up fresh because it's similar to the chapter check-in that you had to do. And I saw a very common mistake where you got the idea of doing the unit factors for each unit equation, but you didn't do the factors quite right, or the equation quite right. So I want to take a minute to go through this. You can work through it on your own if you'd like. But if you looked at your grade from the chapter check-in and you were like, thought I did better than that, stay tuned and watch. If you don't have that equation sheet, this would be a good time. You need those metric prefixes. This is our given value. And we need to figure out how many picometers that is. I see a prefix on both sides of this. So that means I can't go directly from kilometers to picometers. Have to do 2 steps. Kilometers to meters, meters to picometers. Which unit is bigger, kilometers or picometers? Which one is bigger? Yeah, kilometers are bigger. So our answer should be a number that is bigger than kilometers. Because if you think about it, with our pizza example that I use, the kilometer is like the pizza. And the picometers, that's the slices. We've got this number of pizzas. We're going to have a number of slices that's even larger than the number of pizzas we have, just because slices are a smaller unit. So some of you had an answer on your homework, the chapter check-in, that was smaller than the given value. And that should have clued you in that you did something wrong. So don't forget to do that kind of mental math logic check before you hand in an assignment, especially an exam. So the first part of this, we need to have a relationship between kilometers and meters. It's easiest to say that you have one of whichever one has the prefix, right? So in this case, I've got a kilometer. If I have 1 kilometer, then I can replace what kilo means with a number. Kilo means 1,000. So I have 1,000 meters. No one had any issues with writing out unit factors. It was getting the equations that was the hardest part. Now we have to write a relationship between picometers and meters. If I have 1 picometer, then I have 1 times 10 to the minus 12 meters. Some of you wrote 1 meter equals 1 times 10 to the minus 12 picometers, and that's incorrect. If you're going to go with defining this as 1 meter, then you have to flip the sign. A meter is much bigger than a picometer. So the meter in this second example is the pizza. Picometers, that's the slices. So you need a bunch of slices to make up that 1 pizza. If you don't understand that way and it makes sense to you to just replace the prefix with the number from the chart, do it that way. But some people are doing it the other way, which is perfectly fine. But you got to make sure you do it right. So I'll give you 2 minutes, if you haven't already started working on this problem, to set up an equation and get an answer. So I'll check back in 2 minutes. If you have an answer, you can put it in the chat. I'm going to set up the equation here. We were given 2.55 times 10 to the 8th kilometers. We now need 1 unit factor from each of our unit equations. Our plan is to go from kilometers to meters and meters to picometers. Oops. For our first unit factor, we need to make sure to cancel out kilometers, so it needs to be on the bottom. For the second unit factor, we have to cancel out meters, so meters needs to be on the bottom. So we got meters, picometers. When you put this into your calculator, it's 2.55 times 10 to the 8th times 1,000 divided by 1 times 10 to the minus 12. And you may want to use parentheses for that scientific notation. You should get a really big number. So how are we doing with this one? Does this one make sense? Did we get it? Are there questions? Talk to me. So what went wrong? Did you get stuck somewhere? Do you just need more practice? I can't do anything about too many numbers. Maybe it's just too many numbers for this time of morning, too. It's not even 10 o'clock yet. But practice, practice, practice. There are practice problems listed. Okay, so you got 2.255. That is probably because I'm going to guess that something went wrong with entering the scientific notation. You got to remember that negative sign. You will see problems like this on the exam. It's not going to be the entire exam, but you'll have a couple, 3 of these problems. So make sure you're comfortable with it. And like I said, show your work, type it out in the short answer thing. All right, how many people want to do another one of these? Okay. Then here's what we'll do. I'm going to erase this slide and put up a new problem. When I post the notes, I will have both this one and the other one that I do. I just don't have another one of these. At least I don't think I do. Yeah, no, I don't. So I'm going to erase this slide and put up a new problem for us to do. And when I post the notes, both of the problems will be in there. How many centigrams are in 9.25 kilograms. So that's our new question. We set up the problem by first writing out what our question is. So that's our question. We can't jump to any conclusions because we've got kilo on one side and centi on the other. Oh, my bad. Thank you. That's what happens when I make things up. I don't look at my own notes. 9.25. Keep me honest. So we've got kilograms and centigrams. We can't jump straight from one to the other. We've got to use grams as a bridge. These are the two unit equations we have to write. We have to relate kilograms and grams, and then we have to relate centigrams and grams. If you have your chart, you can help me figure out what these equations are. So look at the chart and tell me what I'm putting for the first one. I've got 1 kilogram. How many grams is that? Ten to the third. Same thing as 1,000. Now 1 centigram. How many grams are in 1 centigram? Yes. Now we've got our two unit equations. Okay. From there, we can write the unit factors. But this is key. If you can't figure out what your unit equations are, you will not be able to solve the problem. So how are we doing so far? For all of y'all who are like, me, I want to do another one. Does this make sense? Are we good so far? Okay. We write out the unit factors. Now we set up our equation. Starting with 9.25 kilograms. We need to go from kilograms to grams, and then from grams to centigrams. That's the plan. So when we're putting in our unit factors, we have to choose the ones that will get us from kilograms to grams first, and then from grams to centigrams. For the first one, we need kilograms in the bottom in the denominator to cancel it out. For the second unit factor, we have to put grams in the bottom so that it will cancel out. And always double check. The first one, we get grams, we follow through, and we get centigrams. Now you just have to put it into your calculator. 9.25 times 1,000 divided by 0.01. When you have a number in the numerator, you multiply. Number in the denominator, divide. If you get an answer, let me know. We need units on that. Now, I didn't ask you to write it in scientific notation, so you don't have to. But if you did, so it should have 3 zeros at the end. 925000. Morgan, yes, that's what we're doing. And make sure that you put in all the zeros when you're putting this into the calculator, because if you put in 9.25 times 100 instead of 1,000, then you're going to get one less zero. See, I've been doing this a while. No, you don't have to apologize. That's what this is for. So be careful with that calculator. So we have to move on. If you still have questions and you're able to do office hours, I have office hours from 11 to 1 today. Now we're hitting a question that's a review of significant figures. So we have to add together these 3 measurements and report the answer using the correct number of sig figs. Feel free to go ahead of me. I'm going to write it out and kind of remind you of how we do this. But you can always do the problem and put your answer in the chat. When we're looking at addition and subtraction, what we care about is reporting the fewest decimal places. I like to write it out and line everything up. In school, they may have taught you, oh, you fill in the zeros so that everything works out. Don't do that here because it's going to confuse you. The fewest decimal places. Well, the first 2 measurements have up to the hundredths place, right? 2 places after the decimal. The third one has to the thousandths place. That means we've got to cut it off at the hundredths place. I draw my dotted line, and that reminds me where I need to round. So whatever digit I get here, That's going to be the last one that I keep. And I use the digit directly on the other side of the line to do the rounding. And you add it all together. Then I look at that digit directly on the other side. It's a 9. So that means I need to round my 2 up. And that's my final answer. So hopefully that kind of jogged your memory. We okay with this one? Now you've got to round a measurement to 2 significant figures. And you have to write it in scientific notation. I'll give you a minute or so to do that, and then I'll check back in and we'll write out the answer together. Okay. If you have an answer, you can share it in the chat. So this is our number. If we only want 2 significant figures, that means we are looking at the 8 as our last retained digit. We can keep the 1, we can keep the 8. Everything else has got to go. The digit next to the 8 is a 9. So that means our 8 is going to get rounded up. 19 and 189,000 some odd. 2 very different numbers. So we need to add some placeholder zeros. But we're not done yet. We have to write our answer in scientific notation. For that, we need a coefficient that's at least 1 and less than 10. So you're going to put a decimal right after that first significant figure. That's the 1. So you put a decimal there, you put the 9 there. Everything that is significant goes in this coefficient. Notice how I didn't include any zeros. What's my power of 10? That tells me how many decimal places. Five. So remember, we said here's our decimal point in the coefficient, and we're going to count how many places we need to move the decimal to get it back to its original place. 1, 2, 3, 4, 5. And just to remind you, a positive power of 10 means that your ordinary number is 1 or greater. A negative power of 10 that means your ordinary number is less than 1. So this one covered rounding, placeholder zeros, and scientific notation. Are we good on all of those topics? So now I've put in a sample extra credit question. You'll see something like this on the exam as extra credit. It's extra credit, so you don't have to do the question, but I would certainly recommend that you try it and that you type up your work so that you can at least, if you don't get it right, you can at least get a couple of points, you know? So Chick-fil-A sauce contains 7 grams of carbohydrates per serving. If a serving of sauce contains 140 calories, what percentage of calories comes from carbohydrates? Report your answer with 2 significant figures. And you're given a unit equation. 1 gram of carbohydrates equals 9 calories. There's a couple of different steps for this. So our question is, what percentage of the calories are from carbohydrates? To figure this out, and again, work ahead of me if you're like, I think I got this, or you just want to try it. Otherwise, just stick with me and we'll kind of work it together. The first thing we have to do is figure out the number of calories from the carbohydrates in the sauce. Then we have to calculate a percentage. So we're doing two types of problems here. We've got a conversion problem and a percentage problem. This is why it's extra credit. We didn't do a problem like this in class, although we kind of are right now. But it's recognizing 2 different problem types and being able to put them together and get an answer. So this is for the extra. To figure out the calories from carbohydrates, we've already got our unit equation. 1 gram of carbs is the same thing as 9 calories. So if we want to figure out how many calories, we start with our 7 grams. And then we use a unit factor. We're trying to figure out calories, need to cancel out grams of carbs. So there's 63 calories from carbohydrates. The second part, we have to calculate a percentage. And a percentage is always a part over a whole times 100%. So let me slow down for a second and make sure. Does that first part make sense? How we calculated calories from the number of carbohydrates. Okay. Now for the percentage, we need to have our part, which is the 63 calories from carbs, over the total number of calories, which is the whole, 140 calories. And multiply that by 100%. You should get 45%. Questions on this one? Again, this is an extra credit question. So this is not something that we've done before in class specifically, but it's definitely concepts that you know or are required to know. And if you can put them together, then you can get some extra points. So talk to me. How we feeling? Good. Good. I won't always give you a sample extra credit question, but this is the first exam, and you don't know how I give exams. So this will help you out. Oops. I guess that's it. I didn't put in my normal ending slide because we already did that. Uh-oh. There we go. So do we have questions? It's about 10:15, so we've got another 15 minutes. If you don't have questions, then you're free to go. If you do have questions or you want to try to do another sample problem, you can stick around.